Hello and welcome to section 4.2. In this section we talk about the mean value theorem, but first we need to go over another theorem called Rolle's theorem. And Rolle's tells us that a function that has, if you've defined a function on an interval and it's continuous and differentiable, and the function values at the endpoints of the interval are equal, such as this red function. So Rolle's theorem tells you that if you have a function that satisfies these criteria, there's a number in this open interval where the derivative of the function is 0. So this is telling me if I start here at a y value of 2 and I end here at a y value of 2, if the function's not constant, let's say it's increasing like it is here, then it has to turn around and start decreasing in order to get back to a y value of 2. So in this case, it increases, hits a max, local max, decreases, hits a local min, then increases again. So in this case, there are two values where the derivative reaches 0. So let's identify the part that Rolle's theorem is talking about here with a specific function. So let's look at f of x equals x squared. So my function, and I'm going to look at the interval minus 2 to 2. So a is minus 2, b is 2. We know that that function is continuous and differentiable on that interval. And the endpoints, the y values from the function values are equal they're both 4 at those endpoints. So there's a number c in this interval where the derivative is 0, and when you evaluate it at that number. In this case, c is 0, because I know that the derivative of f of x equals x squared is just 2x, and 2x equals 0 at 0. So that's why we have c equals 0. And this little green dash shows you the horizontal line, which is the tangent at c. Here's another example. It's a little more complex function. A function is this quartic, which has a 0 at 1 and a 0 at 2. So if I make my interval the interval 1, 2, my function is this red solid curve. The endpoints both are 0. This is differentiable, so it satisfies the criteria of Rolle's theorem. So this tells me there's a number c in AB which the derivative is 0. And in this case, it's at 1.5. That's where the function has a local max. So if the function value was 0 and it's increasing, this is just telling me it's got to start decreasing somewhere to get back down to 0. And that value of c is where that happens. So here's an example from the homework. Verify that this function, the sine of x over 2, satisfies the 3 hypotheses of Rolle's theorem, and then find those numbers c that Rolle's theorem guarantees. So we know that the sine function is continuous and differentiable everywhere, so it's going to satisfy the hypotheses that it's continuous and differentiable. And then we test the endpoints. If we evaluate the function at the endpoints, the sine of pi over 4 is equal to the sine of 3 pi over 4. And those are equal to the square root of 2 over 2. So since the y values at the endpoints are equal, this does satisfy the hypotheses of Rolle's theorem. So then we know that there's a number c where the derivative of this function is 0 inside this interval. So if we take the derivative of the sine of x over 2, we get 1/2 cosine of x over 2, and we set that equal to 0 and solve for x, and we get x equals n pi, where n's an integer. Well, in this interval, the only value of n that works is 1. Only pi is in this interval. So therefore, we have c equals pi. And we can see graphically that this little piece of sine of x over 2 on this interval it attains a local max at c equals pi. And of course the local max is where the derivative is 0.